Okay, so basically from the discussion of the logic and proof in mathematics, what remains here is still a couple of things, but the next thing is basically the three different kinds of statements that build mathematics. So there are three different kinds of statements, different kinds of statements that build mathematics. Okay, so and these three are theorems. These three are theorems, conjectures, and axioms. Conjectures and axioms. Okay, so now first about theorems. Basically, a theorem is a mathematical statement whose truth has been established, or we have proved it, and that is basically called a theorem. So a theorem is a mathematical statement whose truth has been established, or proved. That's basically called the theorem. So that's basically something that you have proved. For example, as an example, what they could give you is, for example, the sum of interior angles of a triangle is 180 degrees. So this is something that you can prove. Okay, this is something that you can logically prove. Of course, I'm not going to prove it here, but this is something that you can prove logically, and then once you prove it, that basically that is basically a theorem, meaning that you can use it later to prove other things. So that's basically a theorem. Now a conjecture, Okay, so the next thing that we have is basically a conjecture. Okay, and the conjecture is a statement which we believe is true, based on our mathematical understanding and experience. Based on our mathematical understanding and experience. Okay, which is basically the same thing as some people call it mathematical intuition. Okay, so that is that. Now basically what happens here is that a conjecture may actually turn out to be true or false. That depends on, of course, whether the conjecture, I mean, based on the fact, I mean, depending on the fact that the conjecture is actually true or false, it might actually turn out to be true or false. If you can prove it, it becomes a theorem. So if you can prove a conjecture, it becomes a theorem. Okay. Now, for example, and basically the way that you come across these that you actually make these conjectures is that while you're basically working on something, or while you're thinking about something in mathematics, you basically you kind of see some patterns basically showing themselves, for example, in numbers, or in basically in the theme of what you're working on, and then that becomes the basis for your conjecture. Okay, and then based on those basically patterns, you make some intelligent guesses, and that is basically a conjecture. For example, if you, let's say that you're I mean, in some problem, let's say that you're working on some even numbers. For example, take any 3 consecutive even numbers. For example, any 3 consecutive numbers, for example, 2 plus 4 plus 6, that's equal to 12. If you take, for example, 4 plus 6 plus 8, that's equal to 18. If you take, for example, 6 plus 8 plus 10, that's equal to 18 plus 6 is equal to 24. Okay, so if you take, for example, 8 plus 10 plus 12, that becomes 2230. If you take, for example, 10 plus 12 plus 14, that's equal to 2636. So you can see that these are I mean, all that you can see here, over here, or over here, or over here, or over here, and so on and so forth, and you can just keep going. This is the sum of 3 consecutive even numbers. Okay, and you see the numbers that you see over here are 12, 18, 24, 30, 36. First of all, you can see that all of these numbers are even. And second of all, what you can see is that all of these numbers are actually divisible by 6. Divisible by 6. Okay, so then based on what you see here, of course it's actually, you could simply say that it's based on nothing, because you might actually then keep on going, and then somewhere along the numbers, you might actually come across 3 consecutive even numbers, for example, whose sum is not even, or which is not basically divisible by 6, or whatever other conjecture you have made. But the conjecture that you can make here, meaning that what it means is that actually you're just simply guessing something. So that the possible conjectures that you can make here, the possible conjectures that you can make here is that you can say that the sum of any 3 consecutive even numbers, the sum of any 3 consecutive even numbers is, for example, is even, for example. Or you can say that the sum of any three consecutive even numbers is, for example, divisible by, for example, by 6. Or any other pattern that you might see in these numbers and in this particular situation. Okay? So that's basically that. Now the next thing that we have here, there is also something about axioms. There is something about axioms. Now, I'm not going to so basically about axioms. So basically, so far we have been just talking about proving things and proving everything, and everything has to be logical and so on and so forth. Now there is a question. I mean, a question might arise in you, because if you're then supposed to prove everything, which is almost the case for everything in mathematics, except for a very few things that we do not actually prove. But a question can actually arise in your mind, that do we actually need to prove everything we encounter in mathematics? So do we have to prove everything in mathematics? Okay. And the answer is yes. The answer is yes, but there are certain things that we actually just simply accept without proving them, and those things are basically simply called axioms. So basically these axioms are basically what they are. They are basically self-evident truths. I don't really know how to self-evident. These are basically self-evident truths that basically do not need to be proved. Need to be proved. Other than that, you have to you have to prove, of course, everything else, and that's basically all that mathematics is. You're just basically proving everything, which is well, I don't really enjoy that part that much. But that's basically what it is, and of course it's a wonderful system that everybody has and is contributing to, and so now that it's now become this great body of knowledge, and everything that we have today as human beings is basically based on mathematics, of course. So basically, then you can say that every area in mathematics is basically based on some statements which are assumed to be true, and then you do not simply need to prove them. And these are self-evident truths that do not need to be proved, which are called axioms. And there are, there are some, if you, actually I did a geometry, a while ago I did a geometry course, and if you, for example, I think if you, in probably in 6th, 7th, 8th, or 9th grade, 8th grade, 9th grade, basically grade school, that's basically where geometry starts. It starts from the 6th grade, and then 7th, 8th, 9th grade, and then in basically 9th grade, you usually, depends on the kind of education system that you might be in, or the kind of books that you might be reading. But if you, in the Indian education system, these axioms are usually, this whole business of proving and axioms and everything starts at 9th grade. So in Euclidean geometry, then there is basically all of these axioms that Euclid has taken for granted, meaning that he has actually taken the truth of those basically axioms for granted, and he has not proved them, and then based on those things he has proved everything else. So for example, and there is some other word that has kind of the same meaning in this context, and that is basically called a postulate. So there is something else called postulate, and I do not really understand that there is a difference. I have read this. I have read this word before, and in the context of geometry, I actually got the meaning of this, but now I have forgotten that. So, but it's kind of the same thing, and nowadays the word axiom, the words axiom and postulate are actually being used interchangeably. So you can actually use them interchangeably, although there is some sort of difference between them. But it's not very important for now. Now, for example, Euclid has some axioms and some postulates. For example, one of the axioms of Euclid's, one of the axioms is basically, for example, of course the language is a little bit lame, or at least the statement that I saw was the language was very lame. You would not simply understand the language, but it's kind of something along the lines, if two things are equal to the same thing, the two things are equal to one another. Okay, so that's basically, for example, one of those things that Euclid has taken for granted, and then based on that he has actually never proved this, for example, and then he has taken the truth of this statement for granted. And of course this is something that everybody intuitively knows, so he has taken that for granted, meaning that for example, let's say that you have, I don't know, a length of, for example, a wooden stick, a wooden stick, for example, a certain length, of a certain length. Now, if you have another wooden stick of the same, which is equal in length, let's say that you have this wooden stick over here. Okay, so you have this wooden stick over here, and then let's say that you have another, let's call this A, for example. you have another wooden stick that is equal in length to this wooden stick, call it B. I have another wooden stick, let's call it C, and I know that this wooden stick is equal in length to this wooden stick. If C is equal to A, and also if B is equal to A, then what that means is that these two wooden sticks are actually equal in length, meaning that B is equal to C. Okay, so what that means is that if A is equal to C and A is equal to B, then B is equal to C. So this is something that Euclid has just taken, he has taken the truth of this statement for granted as, I don't know, whatever you want to call it, common sense, intuition, or whatever you want to call it. And then based on this, he has then started proving like 100 different theorems and things. And then, of course, the rest of the mathematicians after him have basically, I don't know, they must have basically, they must have done everything based on his work, because he was kind of the forefather of geometry and so on and so forth. So these are the kind of things that have been taken for granted in mathematics. So one word over here that we need to understand here is the word axiom, and another word is the word postulate. Now let's go over here. The Euclid has a couple things. Let me give you a couple examples here. So for example, the first postulate of Euclid, for example. The first postulate of Euclid. What that is that a straight line may be drawn from any point to any other point. A straight line may be drawn from any point to any other point. Okay, so what that means is that if from any point to any other point, meaning that any 2 points that you consider in a 2D plane, there is at least at least one straight line that goes through those 2 points. Of course, it gets a little bit technical, and you need to be careful about the meaning of these statements. Meaning that, for example, when we say that a straight line may be drawn from any point to any other point, then what that means is that you need to be careful about interpreting the meaning of this statement. Meaning that sometimes it means, for example, there is one and only one straight line that goes from any point to any other point, and so on and so forth, and it could have any other sort of meaning. Once you work with these statements for a while, you will actually get a little bit experience with them. Otherwise, you cannot actually interpret these statements just loosely, the way that you make sense of simple statements in your day-to-day life. You have to be careful with them. Or, for example, the third postulate of Euclid says that a circle may be drawn with any center and any radius. A circle may be drawn with any center and any radius. Okay, so that's basically something that that's something that, well, I don't know, you want to call it common sense or whatever you call it. It's just something that these are called postulates, and these have not been proved in mathematics. Now these statements appear to be perfectly true, and Euclid assumed them to be true. Okay. And of course it makes sense because of course if you were by the, I mean, if you were to go by the assumption that, for example, then you had to basically prove everything, then start working from there, you would be, I mean, for your whole life you would be just working on proving things, and you would not really ever get anything done. Meaning that if I want to, right now, suppose that I'm for example making these statements, I'm talking about these ideas. Now if I were to prove everything that I'm doing right here, or at least to define everything that I'm saying right here, then, so for example, I just said a sentence, made a statement in which there was the word idea. Okay, so now this word idea can have, I don't know, with different people, different kinds of meanings. Probably for everybody has a different meaning, and that's basically the problem that we have with basically communication. Meaning that I understand the meaning of the word idea means something to me, it means something to the person next to me, it means something else to the person next to him, and so on and so forth. And there is actually no way to define things, meaning that at the end of the day, then you would end up with the exact same problem, even if you manage to define everything. Meaning that even if you were to define something, again, in that definition you would have to use some word or some concept, and then that concept would mean something different to me and something different to the person next to me. So again, this is not going to be the problem is not going to be solved. So that means that you actually have to start your work somewhere, and then base your knowledge on some things and take them for granted, just like that. And of course the whole thing actually kind of works out the way that it has, and it has worked out pretty well. It's just like, I mean, that this business of proving everything and defining everything is just like it's just like, for example, the way that, for example, different people see colors. Okay, so we can do everything with, for example, when it comes to a monitor, you can calibrate it, you can do all kinds of tweaking and calibration and everything so that the colors look real on that monitor. But then the problem is that I don't really know, for example, how you actually see the color, some colors, or for example some shade of color that I would call, for example, orange. Let's say that, for example, I have this color, I create this color over here. Okay, so now I'm seeing some shade of, for example, orange over here. And if I were to, I could even go in this program and give you some code for that color, right? But at the end of the day, there is no way for me to know actually what you are seeing, and basically what I have drawn over here. There is no way for me to know what sort of color you are seeing and what sort of color some other person is seeing. So these kinds of things, you have to kind of start somewhere and not get too not get too technical about them. So basically what Euclid has done is that he has started with a whole lot of confusion, of course. A whole lot of confusion, meaning that of course, again, we get to the problem that everybody has different concepts in their minds and so on and so forth, but the whole thing has worked out pretty well, meaning that, for example, we have put all of these things together, and, for example, different engineers, different scientists, and different workers have over the centuries have worked together, and they have built an airplane, or they have built basically the airplane. And today, the airplane does not crash, except for the times that it does, which you might actually be able to find some logical reason for that. But generally, airplanes don't crash. That means that, well, the system that we have is kind of working pretty well. Okay? So that's basically that. So what the whole story is basically the fact that Euclid has started with some basics, and he has taken those basics for granted, and then he has built on top of that, which seems to have been a pretty good decision, even when he's made it. So basically, we need some statements which we accept as true, and then we can build up our knowledge using the rules of logic based on these axioms and based on these postulates. And then of course you might of course ask, so now that we are accepting, for example, the fact that, or this statement over here that says a circle may be drawn with any center and in radius, so I'm just accepting this thing just like that, right? So why don't I accept everything else in the same way? Why do I have to prove everything? Why do I have to basically waste my time like that? And the answer is that, well, basically what we call intuition and common sense, and it kind of, sometimes it kind of, most of the time it actually breaks. You might think that, for example, actually something works. You might actually think that something will actually work. In your mind, you might think about something, and in your mind there is no problem with that logically. But then when you do it, what you will find out is that basically what you thought was wrong, and in reality it's not going to work the way that you thought it would work. So of course you always have to test everything. And I suppose the way that for example, when it comes to physics, for example, there was for example, Dr. Richard Feynman always said that the test of all knowledge is experiment. So you always have to test everything. Now, I think, of course, there is no test for mathematics. So, for example, for example, number 2 really doesn't exist, right? So how do you want to test that idea? So I suppose that the only way that you can test mathematics is just by proving everything logically. If in logic it fits together, then that means that it's going to work. Otherwise, there is something wrong with the logic. And the reason why, that logical proving, I mean basically proving things logically in mathematics works. I think, I'm not sure about this, I'm just making some statement. I think the reason is that, well, the whole body of mathematics is then, of course, then built from the same kind of logic. So if everything fits together, so that means that everything is working together. And again, that takes us to the question why, basically, the question that the famous mathematician asked, and nobody has ever been able to answer that question, which is basically, why does mathematics works at all? And that's basically that. Okay. So, and of course you are also familiar with the fact that, for example, you see some patterns, your vision your vision can fool you, your intuition can fool you. You might even see some, for example, a line segment, the same line segment with the same lengths in different orientations. You might see them, you might actually say that this is longer and this is shorter and so on and so forth, although all of those line segments might be of the exact same length. But if you change the orientation, if you add a few details to the line segments, you might actually, your eyes might actually tell you that, for example, this one is shorter and this one is longer, and the only basically tool that you have in order to see those line segments is your eyes. So when your eyes are lying to you, then of course the only way to make sure that you're not making a mistake is to either for example, to measure those line segments, or prove things logically so that you can make sure that what you're saying is actually right. Okay. So that is basically that. Now, so basically now we said that so we take some axioms and some postulates. We take the truth of those two things for granted, but then everything else we have to prove them. So now there is always the possibility that those axioms and those postulates that we take for granted, they might actually be wrong. I mean, at least in some cases, that they might be wrong. Now, in order to make sure that everything fits together and there is no problem regarding the postulates and axioms that we have taken for granted, there are a few things we do in order to make sure that again we have as little problems as possible. So the first one, we keep the axioms to a bare minimum. For instance, if I haven't actually done that course in geometry here in this mathematics course on YouTube, but based on only axioms and 5 postulates of Euclid. Euclid has basically all the axioms and the postulates of Euclid. If you want to take them together, that's basically not more than 10 axioms and postulates all together. It's about 5 of them are about geometry, 5 of them are about logical things, and so on and so forth. And then based on that, we have derived like hundreds of theorems, and so that's basically, and all of those theorems are basically based on only, for example, only 5 or 10 axioms and postulates. So basically, one thing that we do is that we keep the axioms and postulates to a bare minimum. Okay, so that is one thing. And the second thing, number 2, we make sure that axioms are consistent. Axioms are consistent. What that means is that basically we say that a collection of axioms is inconsistent, not consistent, inconsistent. We say that a collection of axioms is basically inconsistent. Okay, if you can use one of those axioms in order to prove some other axiom in the same collection, if you can use one of those axioms in order to prove some other basically axiom in the same collection, wrong. Okay, so for example, let's say that you have all of these axioms over here: axiom A, axiom B, axiom C, axiom D, and so on and so forth, and that you basically call a collection of axioms. If you can use this axiom D in order to prove that axiom B is wrong, then that means that this collection of axioms is basically inconsistent. Okay, so we make sure that the axioms are basically consistent, meaning that they have to, of course, they have to logically fit together. For example, if you have a collection of axioms over here, suppose that, for example, A says that, for example, the measure of the internal angles, the sum of the internal angles of a triangle is 180 degrees. Okay, and let's say that axiom B says that the sum of the internal angles of a triangle is 181 degrees. So of course you know that basically these axioms are inconsistent. The sum of the internal angles of a triangle cannot be 180 degrees and also at the same time 181 degrees. So it's just basically not possible. So then that's basically called that is called an inconsistent collection of axioms, and you have to take care of the problem. Okay, now the next thing that we do over here is that erase these things. The next thing that we do over here is that we say that a false axiom will sooner or later result in a contradiction. we say that there is a contradiction when we find a statement such that both the statements and its negation are true. Okay, so this is important. So a false basically axiom will sooner or later result in a contradiction. Okay, so contradiction. So what that means is that so basically what the contradiction is, of course, we are going to see practically in proofs what the contradiction is. And there is also something called proof by contradiction. That's actually a way that that's actually a technique that we use in order to prove things, meaning that we intentionally use we use the negation of a statement in order to prove something, and that's basically called proof by contradiction. But for now, we say that there is a contradiction when we find a statement such that both the statement and its negation are true. But of course, if you didn't understand what I said right here, it doesn't matter. We are going to get to that in the next video or the video after that. So it doesn't really matter. But for now, all that you need to understand is that basically a false axiom will sooner or later result in a contradiction, meaning that there will be some sort of logical contradiction, and we will see how this logical contradiction works, and it actually is something useful, meaning that you actually intentionally create that contradiction in order to prove that something, for example, is true or is, for example, false. Okay, so that is that. Okay, so now the next thing that we have here is basically, now we want to see. So now we have basically read everything about a theorem and a proof and statements and false and true and everything else. But now you need to be able to somehow put the whole thing together in order to form a mathematical proof. So now there are basically actually two concepts here that you need to understand, and there is one of them is called verification, and the other one is called proof. Okay, so for example, when we let's say that let me make a statement. So if I were to make a statement and say that, for example, the sum of any three consecutive for example even numbers is consecutive even numbers is divisible by 6. Okay, so now basically how verification works, and we had this before. So So for example, if you were to do verification for this, you would just simply write a couple of numbers. For example, 3 consecutive even numbers would be 2 plus 4 plus 6, and that's equal to 12. It is divisible by 6. For example, 4 plus 6 plus 8 is equal to 18. It is divisible by 6. And 6 plus 8 plus 10 would be equal to 24. It is divisible by 6. 8, for example, plus 10 plus 12 is equal to 22 plus 8 is equal to 30. It is divisible by 6. So then, for example, you test a couple of numbers, and then that way you have verified it, and then you say that by verification, I say that, for example, by verification, I'm saying that, for example, this is, for example, a true statement. But the proof is different, and we are going to see how. Okay, so or for example, even if you take a look at mathematics books related to, for example, 6th grade or 7th grade or something like that, over there you cannot really find any proofs or anything, but there is all verification. For example, if you were to, for example, let's say that you have a statement, the sum of internal angles of a triangle, internal angles of a triangle, okay, is equal to 180 degrees. Okay, and over there, what you usually do, I mean, all the time in 6th grade or 7th grade or something like that, what you usually do, you verify things. So for example, you draw a triangle on a piece of paper, a triangle like this, and then you use your geometry box, and then you, using a protractor, for example, measure this angle and this angle and this angle, and then you call them, for example, alpha, beta, for example, gamma, and then for example, you write alpha plus beta plus gamma is equal to, for example, 180 degrees or something like that. So that is also called that is also basically another way to verify things, using diagrams and things like that. And of course, the problem with verification is that although you might be able to, for example, test, for example, 10 or 20 or 50 or even 100 cases, and just keep adding numbers up for example, 100 different cases, you can really never be sure that any 3 consecutive basically even numbers are going to work in this situation, meaning that you could probably, I don't know, test, for example, 100 different cases. You might add up 3 consecutive even numbers together, and you get some numbers over here which are basically divisible by 6. But then somebody might come up to you and say to you that, for example, I have actually tested these 3 numbers, these 3 consecutive even numbers, and then the sum of them is not divisible by 6. So of course you can never be sure that basically what you're saying is actually always true. That's the problem with this kind of verification. So then, in order to solve that problem, in order to make sure that basically what you're saying is true for all the different possible cases of that particular problem, then you need to basically prove something logically. And the way that works, so basically proving a statement is basically a process is basically establishing the truth of a mathematical statement based purely on mathematical logic, okay, on mathematical arguments and mathematical logic. That's basically called mathematical proof. So how does it work? So first of all, there is basically a very simple way to do that, and that's basically called a counterexample. Okay. So when you want to, in order to disprove a statement, okay, you can use something called a counterexample. Okay, so for example, you basically have some statement A or P, for example, and this statement P says something. Basically, it's a mathematical statement. So you want to prove that it's wrong, or you think that statement is wrong. Now, in order to prove that statement is wrong, it's enough to show one single case in which basically it's enough to get basically one single example that proves that statement is wrong, and then that basically takes care of the whole statement, because we said that a mathematical statement is valid and acceptable if it is basically a mathematical statement is valid and acceptable, okay, if and only if it is either true or false. Okay. So now the way that you can identify whether a statement is true or false, if a statement is always true, then you can say that the statement is true. Otherwise, it is false. Okay? So that's basically how it works. If a statement is always true, then you can say that that's a true statement. Otherwise, it's a false statement. So based on this, if you want to disprove a statement, all you need to do, you can find a counterexample, and using that counterexample, use only one single case or one single situation in which that statement does not work. And then, since it's not always true, then it's basically a false statement. That's basically how that works. So again, to show that the mathematical statement is false, it is enough to find a single counterexample. So for example, if you want to make this discussion right now a little bit more mathematical, but mathematical. For example, let's say that you have a statement that says the sum of two odd numbers is odd. the sum of two odd numbers is odd, okay? And let's say that this is some statement called P, for example. So the sum of two odd numbers is odd. So for example, you can, first of all, most of the time you have to just take a look at the statement, see if it's true or false. Usually you know if it's true or false based on your experience with mathematics and intuition and things like that, and then you can take it from there. Okay? Meaning that if you're, of course, if you're absolutely sure, or if you think that some statement is true, then of course you try to prove it. Otherwise you try to disprove it. So now, first I need to start with some verification, see how this thing actually behaves. Okay? So sum of two odd numbers is odd. So for example, you have, let's say you have 3 plus 5 is equal to 8. So it's an even number. Or for example, I don't know, 5 plus 7 is equal to 12. Now I do not really have to produce an infinite number of basically examples. If I can show even one case, for example, even this one case where I add two basically odd numbers and I get an even number, then that is proof enough to disprove this statement that says that the sum of two odd numbers is odd. Okay, so now let's see how we can actually, this whole idea was basically an idea of counterexample that basically disproves something. It doesn't prove it, and you use it mainly when you want to disprove things, not when you want to prove things. And of course, again, I don't want to repeat myself more than I have to, but when you get, for example, let's say that I have been given this statement. It says that the sum of two odd numbers is odd. Okay, so I have no idea about this statement. So I start by putting together some cases and see how basically the whole thing works out. Okay, and then based on that and then based on my past experiences with numbers and mathematics in general, I can form some idea, and I can say that, okay, so I think that this statement is false, or I think that this statement is true. And then if I think that the statement is false, then of course you can use, for example, the idea of counterexamples and prove it wrong, or then I can actually use mathematical proof in order to prove that the statement is true. Now, in order to prove that a statement is true, you have to put together a proof. Okay? And there are different stages in doing that. Okay? So basically here a list of ingredients. Here is a list of ingredients of a proof, of a mathematical proof. Okay, so first of all, to prove a theorem, you should have a rough idea as to how to proceed. So number one, have a rough idea as to how to proceed. Okay, So for example, what that means is that, let's say that I want to prove that the sum of the internal angles of a triangle is 180 degrees. So what I do is that, let's say that usually when it comes to geometry, you have to draw some sort of diagram in order to be able to see something and think about the situation. So for example, then I draw a diagram like this and say that, okay, so now I have this basically this space over here, and these are the two sides, and the only thing that I know over here is that, for example, this is a triangle. That's all I know. I know that it's a polygon, and it's a polygon that has basically only 3 sides. That's all I know here. I cannot assume anything else here. So now I have to, in my mind, I have to put some proof together, and that proof basically then tells me how to proceed here. So then I could say that, for example, okay, so I can actually draw, for example, some line perpendicular to this line, right? And then as a result of that, I get basically two right triangles. This triangle over here, if I call this, for example, ABC, and call this deep, for example, then I get 2 triangles, ABD and ACD. And then for example, I don't know now, I don't know, basically then you could use different theorems and things related to triangles to prove that the internal sum of the angles of these triangles. For example, you can I don't know how, basically I have done this a long time ago. I don't remember how to do it, and I'm not actually a big fan of memorizing things, and I actually cannot memorize things. And if I do something, I do it in the moment and then I forget it. Especially when it comes to proofs, you don't really have to memorize them unless you have to write a test or something. But it doesn't really matter for now. For now, what I wanted to show you is that, for example, you draw a diagram, take a look at the diagram, and then you say that, okay, so I'm going to do this, and then put this angle over here, and then this angle is equal to that angle, and so on and so forth. Then I'm going to use that theorem, then I'm going to use this theorem, and put everything together, and then that's how I will basically prove the whole thing. Although, I mean, in this particular case, at least right now, I have no idea how to do it. Okay, so that's basically how have a rough idea as to how to proceed. And sometimes, I mean, most of the time, you don't really see the whole proof or the whole solution there. You just see some rough idea, or you actually suspect that something might work, so you start working on it, and it might work, it might not work, so you have to just keep playing with it until you find the right way of doing it. And number two, the information already given to us in a theorem, that is the hypothesis, has to be clearly understood. You have to understand the hypothesis. Okay, and the hypothesis is basically all of the information that has been given to you in that problem. Meaning that, for example, in that particular problem where I said that basically we wanted to prove that the sum of the internal angles of any triangle is equal to 180 degrees, my hypothesis is that that polygon that I have is a triangle. And then based on the fact that polygon is a triangle, of course, then I would be able to assume certain things related to triangles that I have basically proved before, right? So I have to understand basically what sort of information has been given to me in that hypothesis, and then based on that, of course, I will be able to assume certain things based on that situation. Of course, we'll get to a practical example and we'll And then number 3, or part 3 of the ingredients of the mathematical proof, is a proof is made up of successive sequence of mathematical statements. A successive sequence of mathematical statements. Okay, so that is basically that. Each statement is a proof. In a proof is logically deduced from a previous statement in the proof, or from a theorem proved earlier, or an axiom, or our hypothesis. So then, as you have a successive sequence of mathematical statements, now each of these statements is basically logically deduced from a previous statement in the proof, or from a theorem basically proved earlier, or from an axiom, or from the information that has been given to us in the hypothesis. And the conclusion of a sequence of mathematically true statements laid out in a logically correct order should be what we wanted to prove. That is what the theorem basically claims. So what that means is that now what you need to do is that basically you have to put all of the information that you have to put them together in a logical manner, and in such a way that the logical conclusion of all of those steps becomes what you actually wanted to prove. Okay, and that's that's basically what and that's basically what the proof is. So the conclusion put together in a basically logical manner should be what you wanted to prove. That is basically, that is what the theorem claims. Okay, so that's basically that. Now, in order to understand this, and of course this is an intuitive, basically, I mean, well, of course we have broken everything down into 4 steps, and these are all laid out very nice and nicely and basically very very logically together. But at the end of the day, this is something intuitive that you need to put together, and it's not always very simple. And well, usually I, for one, usually try to evade proofs. Okay, I don't like them. I don't, if I don't have to prove something, I don't prove it. But usually I go through the proofs. For example, whenever I'm reading some mathematics books or something like that, I read the proofs in order to see what sort of logic they have used in order to prove that particular example. Because you might actually learn something from the way that theorem or that problem has been proved, either wrong or either true or false. And then you might actually be able to use the same line of reasoning or logic in order to do other things for yourself. So, but I never try to memorize them, and I don't really care about them. As long as I know that something is logically true and somebody else has proved them, of course, it's enough for me. It's proof enough for me that I can use it in my own work, whatever that might be. And then, of course, well, I don't have to worry about any sort of tests or anything, so I don't really care about them that way. But the logical way that for example has been used in order to prove something sometimes is actually very interesting and also useful for doing other things. That is basically, therefore, whenever I come across proofs, I go through them, and in order to basically just simply logically understand them. And that's enough for me. More than that, I don't really need to do. So now we have a couple of things over here. Let me go through. I think I'm going to finish this video, end this video over here. In the next video, we will go through a couple of proofs and analyze them. And still, there is a couple more things here to take care of. So, related to the same concept of mathematical proofs. So I'll see you in the next video.